Hello, good evening to all of you. Hello, I am Saikat Giri, your chemistry lecturer. Today we are going to start about the representation of electrochemical cell. How electrochemical cells are represented with respect to the given reaction. And when electrochemical cell is given, how their representation can be drawn. Both methods we will understand. Let's start with the first topic. That is representation of, we are going to read representation of electrochemical cell. So, how can we represent an electrochemical cell? One basic method we use, that is known as lone. What do you mean by lone? Lone means left oxidation, anode negative. So in the left side there will be oxidation and anode will be present in the left in electrochemical cell. Especially we are talking about here, and N stands for negative. So when we are discussing about galvanic cell, in that case we follow this method, left oxidation, anode negative. It is galvanic cell or electrolytic cell, it does not matter, always anode will undergo oxidation reaction. So how can we represent the reaction? Previous day we have read the reaction about zinc and copper. Let's recall the reaction. Zinc solid plus Cu2 plus aqueous, it gives Zn2 plus aqueous plus copper solid. Now how this cell reaction is represented? For this cell reaction the representation is like, see, zinc is solid and it is being oxidized 0 to plus 2. So in this case oxidation is happening. Cu2 plus 2 to 0. So in this case reduction is happening. So whenever we are representing the cell, in the left side oxidation need to be written. There are some more mnemonics to write the reaction. This line simply means the phase or state of the element. When we are writing state of two elements, we will separate them by this. There is one parallel line as well. This is considered as salt bridge. Parallel line is the salt bridge for the reaction. So in this case we are representing zinc. So zinc is oxidized. In the left side oxidation happens. 0 to 2 plus zinc solid, Zn2 plus aqueous. They are connected through salt bridge. So now I will take salt bridge. From salt bridge what is the representation? Cu2 plus aqueous to copper solid. So in this case reduction is happening. So I will write Cu2 plus aqueous slash copper solid. See, cell can only be made if both the sides are solid only. Otherwise cell representation cannot be done. Let us consider any product we are taking where left side is coming gaseous or right side is coming liquid. In that case how cell can be represented? Let's see in some other examples. Next example I am taking, that is for zinc with H plus. So zinc is reacting with H plus. Let us consider I am taking zinc solid plus 2H plus aqueous. Zinc is at 0. What will happen? It will give Zn2 plus aqueous plus H2 gas liberated. In this case it is plus 1. From plus 1 to 0 it is 0 to plus 2. So from zinc to Zn2 plus it is oxidation. From H plus to H2 it is reduction reaction. How the cell representation can be done? In this case we will write zinc solid in the left side transfer to Zn2 plus aqueous, that is in the right side. Now we will divide them by a salt bridge. We are going to write H plus to H2. Now keep in mind 2H plus is written. we are never going to write any stoichiometric coefficient while representing the cell. So in this case, I will basically write H plus aqueous transferring to H2 gas. But the thing is, the cell cannot be represented like this. That's why we have to take coke, that is carbon compound, or we can take platinum solid as standard electrodes. They are considered as inert electrodes, so if we connect them, there is no effect in the cell reaction is not going to change. As a result, we have to represent in this format. So to represent this complete cell, I need to take platinum solid with this. If I take platinum solid with this, now the cell is complete. So cell representation can be done in this way. Let us take few more examples and we will write how to write down their equations. I am taking Cr2O7 2 minus aqueous. It is reacting with Fe2 plus aqueous, giving the product Fe3 plus aqueous plus Cr3 plus 2Cr3 plus. Now we need to find out the oxidation state of the element, where oxidation, where reduction is happening. Then we will decide everything. In this case, Cr2O7, chromium, we don't know the oxidation state. We are considering as X. 2 is there, so 2X. Plus 7 into minus 2, that is equal to Cr2O7, 2 minus we have taken, so equal to minus 2. So in this case, our X becomes plus 6. So this is at plus 6 oxidation state. As 2Cr is present, that's why we have to take 2Cr in this case. In this case, if you are taking Cr2 plus, Cr3 plus we are taking. Here what happens? Chromium is at plus 6 oxidation state. But here chromium is at plus 3 oxidation state. So change in oxidation state in both the case is 3. But 2 moles are there. So 3 into 2, overall change is 6. As a result, n factor in this case is 6. So whenever we are taking Cr2O7 2 minus, we have to say that in this case oxidation state decreased. As a result, this is a reduction reaction. Iron 2 plus to iron 3 plus, it is oxidation reaction. Now we are going to represent their cell reaction. Left oxidation, anode negative. In the left side, we are going to write down oxidation reaction, that is Fe2 plus aqueous transfers to Fe3 plus aqueous. They are separated by salt bridge, and in this case the compound we are taking, that is Cr2O7 2 minus aqueous transferring to Cr3 plus, that is in aqueous state. But the confusion is, here both are in aqueous state. Cell cannot be represented like that. So in both the direction, I am going to take platinum solid. Here also I am going to take platinum solid. So it is the exact cell representation for this. Few more examples we are taking. We are taking silver with H plus. Let us take 2Ag plus H2 gas. What will it give? This is our question 3. What will it give? It will give Ag solid plus 2H plus aqueous. This is the product produced. How can I represent the cell reaction? Let's check out in this case. If I am taking this compound, so 2Ag plus, this is aqueous state. How it can be represented? Let's check out the form. So Ag plus 2 Ag solid plus 1 to 0. This is our reduction reaction. Here 0 to plus 1. This is oxidation reaction. So in this case, if I am representing the cell reaction, in the left side I have to write oxidation. As a result, H2 gas, and here H plus is aqueous. Connected via salt bridge, this is from Ag plus aqueous, it is transferring to Ag solid. So this is the basic representation. In this side solid is there, so okay, we do not need anything, but here gas is there. As a result, I have to take platinum solid for completing the cell. So these are the basic representation of the cells we represent in this method. Let us consider any type of question is given where they have asked you to find out K for the reaction. Means equivalent for the reaction or equilibrium constant for the reaction if they are asking. In that format, how you can solve the reactions? Is it mandatory that always we have to write in this side oxidation, in this side reduction? It is not mandatory at all. We can write reduction formats as well. I am showing you if someone is writing this platinum solid H plus aqueous slash H2 gas double slash Ag plus aqueous slash Ag solid. Here what is happening? Reduction. So this is the type of cell known as reduction cell. This type of cell is oxidation reduction cell. Here we are representing both in reduction format. This can also be represented. Now let us consider some concentration is given for any compound. How they can be represented. For example, they have given that H plus aqueous is 1 molar. So after this I will write 1 molar. I can give comma. If I don't give, then also okay. I can take one single bracket. Here Ag plus aqueous I can give 1 molar like that. If gaseous substance is there, for gaseous substance it is represented in ATM format. So it can be represented as P1 ATM. Understood? So whenever we are going to write K for the reaction, that is equilibrium constant for the reaction, by following these only we have to write. Let us see further with some more examples. One example for tin, question number 5 we are discussing. Tin solid to SN4 plus aqueous. This is the given question, and here chlorine gas and Cl minus aqueous. This is given in the question, and Pt. Obviously we have to give one solid to complete the cell. In this case, how can we represent the cell reaction? And equilibrium constant is also asked to find out. What we are going to do in this case? Let's take the understanding part to part. See, here tin is a solid Sn. It is transferring to SN4 plus. So SN4 plus is there, so I can write 4 electrons. In which side this happens? You see, one element from 0 to plus 4 means oxidation is happening. We know that left oxidation anode. By seeing this in left side, we are very clear about it that it is an anode terminal. In left side oxidation happens 0 to plus 4, so it is an oxidation reaction. Now what is the reduction reaction? Chlorine transferred to Cl minus. So in case of chlorine, we can represent it like, if chlorine they are giving gas, so it will be a wrong question, they have to give Cl2 gas. So I am writing next, cathode reaction. For cathode, Cl2 gas represented to 2Cl minus, it becomes negative. So it simply means in this side, electrons need to be added. How many electrons? It is 2Cl minus, it is zero oxidation state. So I have to add 2 electron to balance it out. So I can write Cl2, 2 electron gives 2Cl minus. Whereas 2Cl minus has state aqueous, SN4 plus has state aqueous. Now if I add both the reactions, see, addition is not possible, as both are having different number of electrons. First you need to remove the number of electrons. So here 4 electrons are there, here 2. We need to multiply all by 2. So the reaction will become 2Cl2 with that 4 electrons, and it will become 4Cl minus. So the cell reaction becomes tin solid plus 2Cl2 gas gives SN4 plus aqueous plus 4Cl minus aqueous. This is our net cell reaction. When I got the net cell reaction, we can find out K equilibrium as well. What is K for this reaction? We know in case of equilibrium constant, according to Lorentz principle and according to law of mass action, these are explained. Here we are going to use law of mass action. Lorentz principle generally explains the direction of the reaction, and for equilibrium constant, law of mass action are represented. Generally it is represented in terms of activity, but for 11-12 standard, we can represent in terms of concentration and pressure. Let's see, in this case, SN4 plus product concentration divided by reactant concentration into Cl minus whole to the power 4. Why? Why Cl minus whole to the power 4? Because coefficient is raised to the power. That divided by, see, tin is solid, so it is considered as unity. Its activity is 1. Activity represented by small a. Now Cl2 gas. Gas can be represented in terms of PCl2 or in terms of concentration. If someone write like this, it is correct. Or it can also be represented as SN4 plus into Cl minus to the power 4 divided by PCl2. It can be represented like this. So this is the basic representation for a general cell, and we can do the reverse as well. Perhaps I am clear. Let us take one more example, very famous example of Cr2O7 minus. Reacting with Fe2 plus aqueous in presence of aqueous medium, we see this reaction Fe2 plus Fe3 plus. Now Cr2O7 minus aqueous, it is transferring to Cr3 plus aqueous. As it is aqueous, so there need to be any inert electrode added. So this is the format. Now we are going to balance the reaction and we are going to write its cell reaction. See, left is always oxidation and anode terminal. So in my anode terminal, representation is like anode oxidation happens. So Fe2 plus transfer to Fe3 plus electron. In case of cathode terminal, what is happening? Reduction is happening. In cathode, Cr2O7 minus. So Cr2O7 minus. Here chromium is at plus 6 oxidation state. Transferring to Cr3 plus. You have to take 2 Cr3 plus to balance it. Cr2 plus. So it is also in plus 6 oxidation state. In this case, you can find out plus 6 to plus 3, it is a reduction reaction. So here plus 6 charge is there, but in this case overall charge is plus 2. Overall charge is this is plus 2. Sorry, this is minus 2. And this is plus 6. Minus 2, how can it become plus 6? First we have to decide that. Let's balance this reaction first. After that, we will check the overall reaction. Let's take step by step. So you have Cr2O7 minus. In the right side you have chromium 3 plus. 2 chromium is there. First make it 2 Cr3 plus. 7 oxygen is there. As a result, opposite side I am going to add 7 water. At 7 water I have added in this side, 14 hydrogen becomes extra. So I am going to add 14 H plus in the opposite side. Now I am going to check charge is balanced or not. See, 3 into 2 in this side plus 6 charge is there. In this case, 14 H plus and minus 2. So overall plus 12 charge is there. In chemistry, there is no replacement of positive charge. As a result, we have to decrease this charge to plus 6. So there is only one way to do this. I am going to add electron in this side. So plus 12 and minus 6 it becomes plus 6, both becoming equal. Now I am going to write it in the left side, that is the overall reaction is going to be in cathode Cr2O7 2 minus plus 14H plus 6 electron transferring to 2Cr3 plus 7 water molecule. Now we can check here that in this case 14H plus it is completely balanced but 6 electron is there. As a result we have to multiply with 6. Now both the electrons are removed. Now we can write the net cell reaction. What will be net cell reaction? That is 6 Fe2 plus Cr2O7 2 minus plus 14H plus going to give 6 Fe3 plus 2 Cr3 plus 7 water molecule, that is liquid state. This is our overall reaction we can represent. Now what will be K for this reaction? K is product concentration Fe3 plus whole to the power 6 into Cr3 plus whole square, it is liquid state, so 1 not considered. This divided by Fe2 plus, it is in aqueous state, so Fe2 plus whole to the power 6 Cr2O7 2 minus aqueous state, this Cr2O7 2 minus, there is nothing multiplied, it will remain as it is, 14H plus, so H plus is aqueous, so it is H plus concentration whole to the power 14, this is whole to the power 14. So in this way any cell constant can be represented. This is equilibrium constant. For any reaction, if you are representing equilibrium constant, you have to know redox balancing. With redox balancing you can solve these type of questions. Thank you everyone for being with me. If you have any confusion, any doubts in the topics, please comment below. Like, share and subscribe. Let's learn and help people to learn. Thank you.